Okay, hi everybody. Thanks for coming. Today will be the last seminar of the semester, and we're very happy to have Kirsten talking about an enriched excess intersection formula. Go ahead.
Thank you very much. I wish I were in Oslo. Maybe someday. So this is joint work in progress with Tom Bachmann. And please do take this with a grain of salt. We have a paper on the archive that does have excess intersection enrichment stuff in it, but this is a follow-up project. So there's a very famous excess intersection problem, the 3264 problem. And it asks, so given 5 general conics, C1, C2, C5 in the plane, how many conics are tangent to all 5? There's a famous wrong answer and a famous right answer. So the space of plane conics, we've got 6 coefficients, and that up to scaling makes a P5. And if you look at all the plane conics tangent to a single conic, classically one can figure out what's called ZI, inside all the plane conics, those plane conics which are tangent to CI. Plane conics, tangent, TGT for tangent to CI in P5. And this can be figured out to be a hypersurface of degree 6. So if we want conics tangent to all 5, we would say that this is Z1 intersect Z5, and by Bezout, or this would be the Euler class of 06 to the 5 on P5. So let's make this a number, Euler number. We would have 6 to the 5 is 7, 7, 7, 6. And then this is famously not the right answer, because there are doubled lines that are tangent to absolutely every conic. So it's not true that this is a finite set. So this is not true. It ought to be not right answer. Inside this intersection, we could take all of the linear polynomials in 3 variables. That's another P2 or a P2 dual. And we take the square of them, or so L goes to L squared, and that goes inside P5, and they're tangent to everything. So they're also in here. And so this isn't finite. However, so this is an excess intersection. And once we remove the P2, make this. Then we'll write that for now. Z1, Z5 minus P2 is 0 dimensional, is a finite number of points. So the removing P2 and the fact that we then got the expected dimension makes this a 5 residual intersection, or a residual intersection. One can calculate the number of points with an excess intersection argument. There are finite number of points. This number is 30 to 64, smooth conics, tangent to general C1 through C5 over C, the complex numbers. And it doesn't matter which general conics you choose. You have invariance of number here. So it's independent of C1 through C5. That's a very attractive answer and mistake. So let's ask in the vein of using A1 homotopy theory to say things about such questions, not over C, but what about over R, Q, P, QP, fun things like that. And so you can go to talks about this over R. Can be 0. There has to be even. It's not clear what all the possibilities are. But let's approach this from the perspective of using Euler numbers or classes in A1 homotopy theory to say things about this. So let's let K be a field, and we'll have the stable homotopy homotopy theory category over K, and for a cohomology theory. H, we've got cohomology groups. So in nice geometric degrees, let's think about H being motivic cohomology, so that in geometric degrees we'll get Chow, and extended motivic cohomology, so that we can get oriented Chow, and K theory and KO, and Witt theory. And then we're going to work in geometric degrees. Let's let Hn of X be the homotopy classes of the nth maps from the from X to the nth suspension of H. And we could also take a twisted suspension. So for a vector bundle or a class in K0, we've got the geometric degree V cohomology of X, defined as maps from X to the Tom space of V, smash H, and we can keep track of supports in a closed subscheme and put the support there. And so we have these cohomology groups. So we'll get an Euler class in these cohomology groups. And for counting, we'd like an Euler number. So let's push it forward. So we've got pi x to s smoothable LCI. So it looks like a regular immersion followed by a smooth morphism. Let's let this be proper. So then we've got a push forward from the cohomology in degree indexed by the cotangent complex of pi x to h naught of s. And this gives an Euler class. So here's cohomology groups here. And then we've got an Euler class and number. Here, so if we take a vector bundle and a section, then we'll get an Euler class of the vector bundle with support in the zero locus of section, valued in the cohomology theory in H V dual with support in sigma equals 0 of x, given by the map from x to v, which is the section, but we could also do that as a map from x minus the zero locus of sigma to v minus 0, and we can smash with h with a unit map from s to h. So there's an Euler class which reduces to the Euler class in Chow when h is hz. So we could do the Euler number of 06 to the 5. And with theories that are sufficiently, when h is sufficiently oriented, then we can push forward by when V dual and the structure L, the cotangent complex of the structure map have determinant which differs by the square of a line bundle. So let's do so V is relatively oriented by the data of a line bundle and an isomorphism from the determinant of our vector bundle to the determinant of the cotangent complex. So just, for example, the cotangent sheaf over K. And we're allowed to have the two differ by a square in the definition of V being oriented. And the purpose of doing this is that for all of the example theories, we get a push forward from the group where our Euler class lies. So for V relatively oriented and H in the above examples, or HSLC oriented. We have a push forward going from HV dual X to H rank of V minus dimension X of S. So then the Euler number, which we can use to count, and the sigma rho H can be the push forward of the Euler class. Okay, so this is an enumerative quantity in, for example, the following case. So when X is smooth and proper over our field K. V is relatively oriented, and the rank of V is the dimension of X. And let's suppose for simplicity that sigma equals 0 over K, that K is a tall. We'll look at oriented Chow. Then the H0 of K is given by the group completion of bilinear forms. So our number lies in this group, which is the Grothendieck-Witt group of K, which is the group completion of symmetric, non-degenerate, K-valued bilinear forms. Let's have notation. So A in GW of K will correspond to notation. Denotes the element of GW of K corresponding to the bilinear form on the vector space K that takes XY to AXY. So then this Euler number here, and let's leave off these things for brevity, is a sum over the solutions to the equations, cutting out sigma equals 0, of a weight associated to each of these solutions. That's given by transfer, which is explicit on GW of K from the field of definition of Z to K of a Jacobian of our section of Z. So this Jacobian can be computed by taking a determinant of partial derivatives, and we can also see it from the orientation. So where the Jacobian of sigma at Z, this is in the HOM of the determinant of Tx to the determinant of V, like the determinant of matrix of partials of Z, and this is the if we let omega sub x be the determinant of Tx dual, this is a square by the orientation hypotheses, which means if we choose any, local trivialization, we would get the Jacobian as a number in K of Z. If we change the trivialization, we change by a unit in K of Z squared, because we can change the trivialization of this line bundle that then gets squared. So putting this in brackets makes perfect sense. And the trace KZ over K from GW KZ to GW of K, let's say this is separable. Takes a bilinear form and composes it with a trace form from Galois theory, and that remains non-degenerate. So B to K of Z, and then the sum of the Galois conjugates to K. So it's a computationally explicit weight attached to all of our solutions. So this here, in fact, since we pushed forward, this does not depend on sigma. So I shouldn't have written that. Thanks. I mean, sorry. Because we forget the support. And one can show that that does not depend on sigma on the section. So the fact that it doesn't depend on sigma gives invariance of number enumeratively. And this, it's a count of the set here. It's a weighted count. It's a weighted count of the solutions to sigma equals 0 in bilinear forms. We'd like to compute this weighted count, and then we learn things about the fields of definition of our solutions and about this Jacobian, and it enriches the enumerative geometry count. So here in this, we had no excess. And let's talk about excess intersections. So they happen when the intersection is larger than you think, so larger than the rank of, so the dimension of X minus the rank of V. Let's look at a vector bundle again with a section of a vector bundle with the rank of V is the dimension of X. And we'll take a connected component of our solutions. And this doesn't need to be a point. When it isn't, we have an excess intersection. Or just because of this. We would expect the dimension to be the number of variables minus the number of equations. So we can start removing it. So we'll let I be the ideal sheaf of Z, and then I contains the ideal sheaf of sigma equals 0. So we'll let J be the ideal sheaf of sigma equals 0. And to remove it, we could do that as a set, and we'd like to give it a closed subscheme structure. So the colon ideal, J colon I, is the sheaf whose sections are the elements, the regular functions X, such that Xi is in J for all I in I. And topologically, this is, so think of this as we take out, from the solutions, we take out I and take the closure. Take out the vanishing locus of I, which sorry, Z here. And then we take the closure, and this is really the sheaf of ideals on it. If W, which is the vanishing locus of K, has codimension, let's call the rank of V S. Well, actually, I guess it doesn't matter yet. Actually, yeah, let's do it now. Has codimension S, then W is called an S residual intersection. We're gonna, we're not quite to an answer yet. So let's add another page. Okay. So let's look at the contribution to the Euler number from our residual intersection. So we had this piece in our previous example. We had this large component, this P2. We remove it, and let's look at the contribution to the Euler number from the residual piece, which is the same as looking at the contribution from the excess piece. And we're going to do this in a first case, which is when the closed subscheme is a regular embedding. So then it has a normal bundle. And Zx. The sigma like this gives us a map from V dual surjecting onto J, and also surjecting onto J mod J squared, which is the normal bundle. Dual. So we turn this around and we can define the excess bundle by the quotient. And this depends on sigma. So this depends on sigma. If there's an orientation of V, you get an orientation of E sigma. This is on Z, on the excess piece. And the contribution to the Euler number. So of V sigma is the push forward of the Euler class of this excess bundle. So this is the contribution to the Euler class from Z. And for oriented Chow, it's work of Fazell, and there's in Chow before this, and Deglege and Kahn. So there are people before and people after. That's a wonderful case, and here are some issues with it. The first issue is that this isn't a formula for this Euler class, and classical ways that you usually compute it don't pick up the extra quadratic information from the growth and decay group. I'll summarize that. You'll see in a second. This isn't a formula for what, or we can just say the number even, for what this contribution is. And then issue number 2 is the hypothesis is frequently not satisfied that you had a regular embedding. So the truth is that inside Z, this appears with non-reduced structure. So in fact, it's the closed immersion given by the square of the ideal. Cutting out the Veronese. And since this is codimension greater than 1, when you square an ideal, we're not getting regular embedding. So because there was a multiplicity on our excess component, our our case where we had the regular embedding isn't going to apply. So issue 2 is that the intersection, or Z, W2 for that matter, but Z to X is frequently not regularly embedded. So I'll do an example to talk about this. So an example to approach issue 1, let's let, we'll have a P2 linearly embedded inside Pn. Linear, in fact, let's just call this proj. Okay, well, we'll deal with that in a second. Here's so we've got a P2 linearly embedded in Pn, and question for Q1 through Qn, general degree 2 hypersurfaces containing the linear P2, their intersection is in general a finite set of points and lambda. So the intersection of the Qi is lambda disjoint union W, where this is a finite set of points. How many points are in W? In fact, I'll just actually give it as an answer, because we saw that the excess contribution depends on sigma. So we don't have invariance of number automatically, not from the formulas that we have here. So here we had an invariance of number because the whole Euler number is invariant, and the whole Euler number is the sum of the excess piece and the count of W. So, but the excess piece could potentially depend on sigma. However, like in the 5 conics problem, it doesn't. We have invariance of number anyway. W is a set of, and the answer is 2 to the n minus n choose n minus 2 minus n choose n minus 1 minus n choose n reduced points. Over C. So to find W, what you can do, so this is proposition 13.5 in Eisenbud and Harris's book, 3264, like the 3264 problem and all that, over C or an algebraically closed field. The degree 2 hypersurfaces give us degree 2 equations. So it gives us a section Q1, Qn of a direct sum of n copies of O of 2. And we want to know the contribution from the excess piece. And we get, for the excess bundle, is defined as the quotient of the normal bundle of the excess piece in Pn. to V to the excess bundle on this P2. And we can figure out what the Euler number of the excess piece is, which a priori depends on sigma, but this is determined by the multiplicativity of the Chern character. So we have 1 plus 2 is the class in degree 2 for one of these. So we've got 1 plus the first Chern class here to the n, and then the normal bundle, this is O of 1 to the n minus 2. So we get 1 plus zeta n minus 2. And I'll let you believe that when you do the combinatorics, you can find that the excess piece is always this. In particular, it doesn't depend on sigma. Now, what about I guess I need one more page. What about trying to record the fields of definition of these solutions, the points in this quadric, in all these quadrics? So now release no longer assume that K is algebraically closed, use HC twiddle so we now ask for a weighted count, the count of Z and these intersections. I guess we called it W. The count of W and W and here's an answer. Well, first let's find the problem. So we still have that the Euler classes would be multiplicative, but dividing in, for example, the Grothendieck bit group does not allow you to solve for the Euler number of the excess bundle. So what you can do instead, so this is equal to the Euler number of V minus the Euler number of the excess bundle. And this is 2 to the n over 2 times the hyperbolic form. But we need to figure out this, and you'd want some sort of substitute for this sort of argument, which no longer works. So I'll tell you the substitute. I should hurry up, and I'll tell you the answer. So here's the fix. You can compute. So we wanted to know the Euler number on this, and it is a very pretty fact that to compute the Euler number on this, you can compute bilinear form coming from coherent duality. So the Euler number is computed by a pairing of a coherent duality pairing on H1 in coherent cohomology of E sigma tensor L that that by the orientation is going to land in the top cohomology of the canonical bundle. And this has a map to K. It's computed by this, and you can explicitly compute this cohomology, this cup product, and this trace pairing. So here's the answer. So the excess bundle is going to be a class of a bilinear form B sigma. We're going to let n be odd, and m is just notation for n-1/2. The linear subspace, we'll say it has coordinates x0, x1, x2 in coordinates x0 through xn. This means that the general degree 2 hypersurfaces containing this P2 are a sum of x0 times something linear, x1 times something linear, etc. You can put all of those linear things in a matrix, and then there are 3 principal minors. So this is some sort of big long matrix, and you can take this piece, ignoring the last 2 rows. You can take this piece, and you can take this piece. And if you let the Fi be their determinant, then you can form a local complete intersection ring with these Fi. Generically, the only solution is 0 here. And the duality, a duality result that we'll come back to, there's a duality result for local complete intersections, says that we have a nice pairing. This nice Gorenstein ring comes with a nice description of the trace pairing. So we'll let eta from Q to K be a K-linear map that sends the Jacobian just of F1, F2, F3 in the classical sense to the dimension, and let K, X0, X1, X2, D be homogeneous polynomials of degree D. And then we'll let trace take a homogeneous polynomial of degree 3 and -2, -3 to K to just be eta of F bar. This really is the trace in the sense of coherent duality. And then in the Witt group, this is the Grothendieck Witt group divided by hyperbolic forms. The class of the excess bundle is given by this matrix. You take polynomials of degree m-1, and you take n-2 copies of them, and you divide out by the image of the matrix M. And this is just a little transpose. So this is the space that your bilinear form is on. It's just a bunch of nice explicit polynomials, a quotient vector space. So it's a map from this across itself to K. And in the kth slot, we have a polynomial, and in the lth slot, we have another polynomial. And that would determine this whole bilinear form. And it's the trace. So this is the trace of -1 to the K plus L, HH prime, this determinant, and this determinant. And we get that this weighted count of the residual piece, the residual intersection is, well, minus this class, because that was the excess count. And you can program this into a computer. So here is some Macaulay 2 code. So in out 8, you can see how there are a bunch of zeros because we actually had a quotient space. The bilinear form was on some polynomials quotiented by another image. So there it is, you can compute it. And because it's very explicit, we don't have invariance of number. So remark, there's Macaulay 2 code, can compute this. And invariance of number fails. So it really does depend on the degree 2 hypersurfaces you choose, what kind of weighted count of your solutions, field of definition, and this. So heading back to the 3264 problem, it becomes more of a question about whether we have an enrichment of that problem. Question, do we have invariance of number and I mean enriched in quadratic forms? The difference between the Witt group and the Grothendieck Witt group is not important here. We know the rank from the classical case over C. So for all intents and purposes, this isn't an interesting difference here. In the 3264 problem, issues 1 and 2 are present here. So this was, how do you compute the contribution from the excess? And this is, hey, the excess isn't even regularly embedded. But the answer is yes. So this is this example here is part of the joint work with Tom Bachmann that this talk is on, and so is this answer here. So yes, for K, a field, characteristic K not equal to 2, C1, C5, general plane conics, then irrespective of how you chose them, as long as it's general, then the number of smooth conics tangent to all 5 has this enriched count that's invariant. So the sum over the smooth conics C tangent to C1, C5, we know there are 3264 of them, but if we record how many of them are real and how many of them are complex, of a weight, then we get 3264 over 2, 1 plus minus 1. Okay. So I'd like to use the rest of the talk to discuss tools for approaching issues 1 and 2. Sadly, these tools do not directly give this answer, but Scratch and Sniff does. And we can see some examples that do as well, although I don't think we're going to make it with the timing. So to approach issues, tools to approach non-regular embeddings, non-regularly embedded excess components. And also just for its own interest. So a scheme is Cohen-Macaulay if its local rings are Cohen-Macaulay when they're dualizing complex. For duality, like Serre duality on coherent sheaves is a sheaf in a single dimension. So we'll let omega of x denote that sheaf, the canonical bundle. And a complete local intersection is even Gorenstein, so its canonical bundle is a line bundle. And the complete local intersection, like the quotient ring that turned up in the previous answer. So for a local complete intersection, R, your Gorenstein, so your self-dual, and there is a canonical given by the Jacobian. Is the canonical. And resulting perfect pairing using the Jacobian. And this is classical, but some names that I associate to this are Scheja Stork and Eisenbud Levine, and that's not a great attribution for this stated like this. But it says that local complete intersections are even better than Gorenstein. They're having a canonical perfect pairing associated with them. So Eisenbud and Ulrich generalize this to a canonical pairing when you're not a local complete intersection. So when you could have some excess. So Eisenbud, in a recent, they have two papers, and the first one is the work that inspired this work. So Eisenbud Ulrich, building on work of Hunicke, Van Straten Warnt, and Ulrich generalized this, giving a duality results for coherent sheaves. So here's their theorem, or they show many things, but here is a theorem that it can be generalized to then say things about excess intersections in a one homotopy theory. So let R be Gorenstein local. Let J A1 AS be an ideal. We'll choose some potentially excess component cut out by the ideal I. So I ideal of codimension G. And we'd expect G to be S, but it might not be, and we'll set T to be S minus G. And we'll suppose that once you take out this excess component, you have a dimension S piece. We call that an S residual. So this is let, and this is suppose is an S residual intersection. And they introduce weak, standard, and strong hypotheses. And there's quite a bit of flexibility about the hypotheses. This is the combination of asking that you have a lot of regular sequences, or that the number of generators of I at any, when you localize at any prime P of codimension less than or equal to S minus 1, the number of generators of IP is less than or equal to the codimension of P, which gives some nice sequences and some more mysterious depth conditions on R over I to the J plus 1 that give you that this will be Cohen-Macaulay. For example, the 5 conics problem satisfies the weak hypothesis. So let's leave it at that. And their paper spells out what this is. So then there's a canonical isomorphism. From the T plus first power of I over ITJ to the canonical sheaf of K. And the T equals 0 recovers the LCI case. And this also gives, there are also then canonical perfect pairings on the intermediate powers I to the U plus 1 over IU compare with the T plus 1 minus U piece. So that this gives rise to a canonical perfect pairing as well. Okay, so we remove the hypothesis that R is local and record the dependence on, so we remove the hypothesis that R is local and record the dependence on AI. Theorem, let X be a Gorenstein scheme, let J be a sheaf of ideals which can be locally generated by S elements. Suppose KJI is an S residual intersection. Satisfying the strong hypothesis. Let W equal VK, then there is a canonical equivalence. I t plus 1 over I t j to the suspension of the dual over OX of OW times the determinant of this has to be locally free under the hypothesis. This is locally free. And although this is has this codimension of G, this is locally constant on the intersection of W and the vanishing locus of I. So this winds up being a coherent sheaf. And we can use this to then push forward. So there's also a perfect pairing on this. And so sending a perfect pairing with values in this to its coherent duality push forward. So let's say, so push forward. So X is above, and now we'll use a vector bundle. So this is a rank S vector bundle. And this is dimension S. And V is the ideal determined by the vanishing of the section. So then, again, satisfying the hypotheses of this theorem, then for the residual intersection, we can push forward a perfect pairing. I'll denote those perfect pairings by GW over JIT. We can push them forward and obtain a pairing shifted by S with values in the determinant of the dual, because this was V pulled back to K, and we get this map, which can then be used to create a pairing in here. So here's a residual intersection formula. I apologize for the time. This is we're basically there. So suppose in addition that dimension of the vanishing locus of sigma is equal to 1. Then we have a pairing ij cross ij to I squared over ij. It's a perfect pairing. And the formula is that in the Witt group, WK, we have N of V is the class this perfect pairing, or I star I over j is equal to E V sigma KO. So this is only the piece from the residual, but in the Witt group, the one-dimensional piece doesn't matter, and we obtain this. Well, let me just make two remarks. Warmp's thesis implements in a program called Singular, calculating this, and the difference between the Cazul complex of sigma, which gives the Euler class, and ij. So I really like this remark. So remark the Euler class of V, which is represented by the Cazul complex with a particular pairing, and I over j differ by an algebraic surgery. All right, thank you for your patience. I'll stop there.
Okay, thanks so much, Kirsten. I think we have some time for some questions. So let's open it up to questions. Just go ahead.
Could you say a little bit more about this failure of constancy of numbers that you mentioned?
So the t being locally constant.
Yeah. No, sorry. It's in the example with containing the plane.
Here.
Yeah. Yeah. Exactly. The remark.
Yes.
Do you know how, if you move the equations around, how this changes? Or?
Yes. Well, this is so explicit that I'd say that this is how it changes. So the Q changes these elements of M, and here is a determinant here. Well, I guess this is going to be a yes and no. I mean, this is a formula for exactly what it is, and then you can compute invariance of this resulting sum and discover that they're different. And then if you wanted a more high-level intrinsic description of what happens when you move the QI that's less sort of an enormous computational mess, then I don't know.
I'm sorry. I would like to know. Do you need something like a Chow group of singular schemes, or what? I mean, if you want to treat singular schemes, what kind of group your Euler class live in? Thanks.
Well, I mean, that's a great point. I'd like to view everything in SH, which I mean, I know they're not smooth, so they don't literally live in SH. We could unate it. It seems dubious to me, but we have these definitions here, and yeah. So maybe in all the applications. So I mean, we could just say for X anything, it has some sort of functor by the Oneta embedding, and we could stick it in and use these representable things. but I think, let's go down here. For this, let's suppose X smooth. Because then we had a perfect pairing on something that's potentially not smooth. That's not a problem. We have a way to push forward incoherent duality. But then when we want to look at it as some class here, I think I'd be more comfortable, instead of saying X Gorenstein, saying X smooth.
Okay, we have a question from Oliver Rundigs in the chat. I'll read it out for the recording. Given 5 real conics, does your computation of 3264 tell you how many of the tangent conics are real?
So it can vary with the choice of conics, and it's a weighted. So like the number of real lines on a cubic surface. So where did it go? Great. The number which is literally real would be picked up by applying the signature to the trace of 1. And instead we have the trace of something else. So literally no, but a weighted count of how many reals they are is then 0. And that's what this says. And the number that are literally real does vary with the choice of conics.
Okay, great. How about some more questions?
So von Strottenbaum's paper has a nice discussion of like looking at singularities and looking at the Milnor fibers of these singularities using this pairing in the last case that you were talking about. Have you thought about this at all and trying to like relate it to like an A1 number? Not at all.
Not at all. But this is great. The strong hypothesis is automatically satisfied, so this is a much more geometric thing. Oh yeah, I should have said advertise. We don't have to assume the strong hypothesis anymore. It's then would have been better to write all of this out, but we get to drop strong hypothesis, but we have an S residual intersection, and T is 1. So this becomes much more concrete, and without knowing linear algebra, you can know when to apply this last this last intersection formula. But we haven't done any of the geometry that Van Straten-Warmpt does. You can explicitly compute this for like Euler numbers of vector bundles, but we haven't connected that with any of those nice applications.
Thank you.
So I have a question. Do you have this assumption there that the dimension of the zero locus is 1? What do you get if it's not 1? Like, I imagine you get like a bigger pairing if it's like bigger than 1, maybe. Yeah,
I very much sympathize with that question. So and I just don't know. It would be much nicer to have a contribution. We want the Euler number to be a contribution from I and a contribution from, or the vanishing locus of I, we were calling that Z at one point, and a contribution from K. And this is looking like this is a contribution. This is supported on K. This is supported on the residual intersection. This W, which is the vanishing locus of K. And you could make a kind of moral reason that may or may not be true, which says, well, hey, if your dimension was 1 and you could have an excess bundle, then it would be the Euler number of a one-dimensional bundle and it would be hyperbolic. So we don't have to know what it would be on the z piece if we just compute in w of k. And so that's sort of a way to get around having a guess as to the piece coming from I. And then if you drop this, we don't have a guess.
Oh, okay, thank you.
Thank you. Yeah.
Okay, further questions? No? Okay, well, that was an excellent talk. Thank you so much, Kirsten. Let's give a round of applause for her.
Is it appropriate to thank the organizers of this seminar?